many students you have? You have five.
Five.
Two
are absent today.
Okay.
Why are they absent?
For university exams.
Oh, university.
exams. Okay.
Oh, university exam is at this time?
University.
Yeah.
Which university? Oh, Yale? Oh, University of Hong Kong. Exam, no?
It starts.
Okay.
Okay, so you will have 10 minutes for the presentation,
Okay.
and I will give you 2-minute warning before the end.
Okay.
Let's start.
Good morning, professors. Our topic is cutting twisted solid tori. So our project concerns about generalizing cutting in Mobius strip. And Mobius tells us that when they cut a Mobius strip, we obtain one paper loop but not two. And we decided to generalize this problem and to cutting a twisted solid torus, which we call TST. So what's a twisted solid torus? So we consider a cylinder with the left end twig fixed, while the right end twisted by 2 pi tau radians, and then two ends are joined. And then we model this using a coordinate system to arrive at our mathematical definition. And the tau in our definition is called a twist turn. And this is the very rigorous mathematical definition of our TST. And it is defined as a set of curves, two of which is represented here. And so the next thing is how we cut our TST. Well, and we have a model here to illustrate the procedure. So I will use a TST of twist turn 1/6 as an example. This is the cylinder, but we do not join the two ends because it's hard to do so. So remember that the two ends are joined. And then we will have to choose a denominator for our twist turn. Let's agree to choose 6. We have to choose the number of parts to be cut into, and we choose M 3 parts, which means that M equals 3. And so the next thing is we insert the blades at cross section at the left end. So here are the blades. If you want to see the cross section, this is how we do that. So basically, we define the arc from here to here into 3 parts, and then we now have one point and the other, and these are where we insert the blades, and the blades should be perpendicular to the chord from the arc from 1 to exponential of pi I over 3, and so that they will look like this in the cross section, and in 3D they will look like this. The next thing is we will let the blades run through the height, and then we rotate while rotating the blades. Yes, this is how we rotate the blades. Can you show how it rotates? So these are those are trajectories of the rotating blades. And then we will let the blades run through to the height, the other end of the height. And then because the two ends are connected, the blades will come back to where they have started. And then after rotating a lot, then they finally will come back to where they originally are oriented. And the cross section at the left end is something like this. And we call this graph of the TST cutting the lambda n tau d tau m. At the n tau is the numerator of tau. So just now the case here is lambda 163. And so what do we obtain after we cut that? Well, we will obtain such objects called knotted TSTs. And these knotted TSTs can have their twist turns defined and calculated. And these two turns shall represent the amount of twisting in the knotted TSTs. And we decide to use a multiset to contain all these knotted TSTs, so that the number of each type of knotted TST is the same as the multiplicity of the knotted TST in the multiset. And multisets can be added, just like putting two multisets into one, and then we sum the number of elements inside it. So our problem is that we found that there are in fact only two types of knotted TSTs formed up to twist turns. They are n tau and tau. N tau is the numerator of the reduced form of tau. And we call the number of knotted TSTs of twist turn n tau p, and that of twist turn tau I. So our problem is to find the number of p and I, which are non-negative integers. And we found that we can in fact infer the numbers from the graph we obtained. So for example, in this example, the three knotted TSTs of twister n tau, which is 1, are here to the regions with blue smileys, and those that with twister 1/6 is adhered to the phase with the orange smiley. And so we will obtain this result as our, this sum as our result. And this is the general formula for I. And how about P? Well, P is much more complicated, but we can use a lot of results to find the general formula for P. And we use this formula, we can calculate the number of the P from the number of phases in the graph. And due to a result of Euler, we can calculate the number of phases from the number of vertices and edges in the graph. And for the number of vertices and edges, then we have to use some combinatorics. But we have to consider two more big problems. The first is, well, can you count how many intersection points in the red ellipse? I think that's hard. The main question is that there may be 3 lines intersecting at one point. So we have to consider when are 3 lines concurrent in the graph. And because we are formulating everything in complex numbers, using a 3-line concurrence are very difficult in terms of complex numbers. But if we consider the poles of these lines, which are just points, then this is much easier. And we note the fact that the 3 lines are concurrent precisely when the poles of these lines are collinear. So we are able to derive this necessary and sufficient condition for the collinearity of the poles. And for this equation, we have to find solutions. And general solutions are given in a result polen, but not all these results are useful. So we have to consider which solutions are suitable for our problem. So we have to do some case-by-case analysis, and this is illustrated in Appendix 4. And the next question is to consider the number of when the lines intersect outside the unit circle. And this is known as our second big problem. And we can easily find the necessary and sufficient condition as well, because we are parameterizing every line in our graph. And so having these 2 problems solved, we can now deduce a general formula for P, and these are the results. Okay, so we can also consider some how about questions. And so the first one is, how about if tau is irrational? And the result can be found in our paper. And the next is performing the same cut operation on a different TST, because we found that the cut operation in fact depends on the twist turn of the TST. So that's a question that it is worth considering, and this is the result. The next thing to consider is how about the link that is formed after cutting the TST? Well, if you have a TST with twist turn 1/2, and then we cut it into 2, then because we know that in fact the TST with twist turn 1/2 is the same as a Mobius strip, so we can use a paper model to illustrate this, and that is our link, which is a trivial link, trivial knot, and we can also consider if our TST is of twist turn 3/2, then this will be a Sheffield knot. And for a general result, we can express that in terms of Baywards, and these are the results. Yes, and from these Baywards, we can also find the Cipher matrices, and from these Cipher matrices, we can find the Alexander polynomial. But we are not able to prove that the case for M is hard to be held, although it in fact holds for mu p n tau and mu p d tau ranging from 0 to 10. But the other cases have to be conjectured to be true. So how about if we start with a link, a TST that is not in the form of a trivial knot, may not be in the form of a trivial knot, but a TST link. Then, for example, if I have a TST, make it in a truffle, and then cut it just like we cut any kind of TST just now, then we obtain a so-called TST link on a TST link. And for a TST link on a TST link, then the results can be also expressed generally in terms of Baywards, and these are the results. And so now we consider cutting a TST link, which is in the form of a TST link. So how about if we start with a TST link on a TST link and then cut it? But then we have we can keep this process going on, and we can consider the links that are formed. And we define it inductively that S0 is a trivial knot, and Sn plus 1 can be defined from Sn by having a knot in Sn, and we cut it, and then consider all the links that are formed. Then we have such a TST link hierarchy, and we derive some properties for that. And we also generalize the problem to cutting projective planes and Klein bottles, and these are the results and of the links that are formed. And finally, let's conclude our project. And we derived a lot of results concerning the TST and TST products cutting and the links that are formed. And through our journey, we also developed new results. And we hope that this will open up new directions in research. Thank you.